1987, there were some different versions, and obviously now we're running version 3. But you don't have to do anything different. You just put on OSPF. It's not like RIP, where you actually have to physically go in there and change the version number. All right. Obviously, every kind of protocol has its own header. So just like everything else, OSPF has its own header. Its header has information like the router ID, the area ID, and some other stuff. And there are 5 packet types that we're going to talk about with OSPF. So first, let's talk about how OSPF works. You know, EIGRP, the one that we covered last week, looks at all the routes and the bandwidth and delay and calculates the best path for each individual router calculates his best path. And that's why it's very processor intensive. OSPF doesn't do that. What OSPF does is, I guess a better example, let's say everybody in the class has their phone number on a 3x5 card, and you wanted to know everybody else's phone number. You could either A, have everybody run around and talk to each other and get all their phone numbers and write that down on a piece of paper. So you get up and you ask the 29 people in the class, and somebody else gets up and he asks the other 29 people in the class. So everybody kind of creates their own stuff. That's what EIGRP does. Every router creates his own information based on what he talks to other people about. But OSPF doesn't do that. What OSPF does is says, hey, let's take one person and have that one person run around the room and get all the addresses, make copies of that, and then give it to all the other ones. So OSPF picks a central point, and what they refer to that, they call it the designated router. And then everybody sends information to the designated router, and then he makes the decisions on which paths are best. Then he sends that out to everybody else. So I hope that helps you kind of distinguish between EIGRP and OSPF. EIGRP, it's kind of like every man for himself. OSPF, it's like, hey, let's have a central place where we put everything, and then let's let him make those decisions. Alright, so moving on. Here's the packet types. Obviously, the first one is a hello. And hello just says, hey, I'm here, and it builds those, what they refer to as the adjacencies. It builds the neighbor relationships. If I'm in OSPF and somebody else is in OSPF and he sends me a hello, we will start to try to form a neighbor relationship, and hopefully everything works out. Alright, next one is the database description. This is kind of like, I want to say cliff notes for the database. So when my router starts up, he looks at his OSPF and says, hey, here's the routes that I have. And he builds a very small packet with just kind of the minimum information needed about the different networks that he knows. And he sends that out. And that's the database description. It's just like, again, a summarized version of what he has in his OSPF database. And I send that to my neighbor. Now, my neighbor looks at that and he sees something that he doesn't have in his database. And when he does, then he'll send me a link state request or an LSR. The LSR says, hey, I noticed in your crib notes that you have information about blah. Could you send me the entire information about blah? And then you respond with a link state update, an LSU, and say, okay, here's all the information I have about blah. And then the link state acknowledgement is just how we reply to everything else. You know, when I send you a link state request, you send me an acknowledgement, I got your request, then you send me a link state update, but you get the idea. So, hello. Every 10 seconds by default, just says I'm here, and it's kind of a keep alive and a way to form the neighbor relationships. Database description, just the cliff notes. Hey, here's a very summarized version of what I have in my database. If you see something you like, let me know, I'll give you more. Link state request, hey, I saw something I'd like, give me more. And link state update, oh, here's your more. I hope that helps. Alright. So again, the hello packet just discovers neighbors, establishes those relationships, and then everything starts to work together. Alright, so in OSPF there are 3 things that have to match in order for the 2 routers to talk to each other. And the first one is the hello interval, second one is the dead interval, and then the third one is the network type. So again, hello interval is just how fast I send hello packages. And it's 10 seconds by default. So if you go to one router, like let's assume you go here to R1 and you go to 0000 and you change his hello time to 15, he will not form a relationship with R2 unless we change the hello time here. So the hello timers have to match. The second one is the dead timer. Like EIGRP has hello and hold timer. OSPF only has hello and dead timer, but they do the same thing. The dead timer says this is how long I'm going to hold it until I kill it. So if I don't receive anything, a hello package 4 times, then it's considered dead. So the dead time is 4 times the hello. So going back to EIGRP, hello time is 3 times the hold, and in OSPF the hello time, or 4 times the hello time, is the dead. So I hope that works out. Alright, and then the network type is pretty easy. It's just what kind of network am I connecting to? Am I connecting to a point-to-point or a multi-access kind of network? So most of our labs we're all going to do point-to-points. But here's something that you do need to write down. The IP address used by OSPF is 224.0.0.5. Remember, EIGRP sends on multicast 224.0.0.10, but OSPF uses 224.0.0.5. Alright. Alright, in the hello packets, there's the information used to I guess, elect that designated router. Remember, that's the person that runs around and gets all the information and then puts it together and sends it back out to everybody else. But just like everything, there's always some kind of redundancy built in, so there's also a backup designated router. Alright, and we discussed the network types point-to-point or multi-access. In multi-access, there is an election and a DR is elected. But in point-to-point links, there is no designated router elected because these two routers are going to talk specifically to each other, these two just to each other, these two to each other on those points. So each point only connects to 2 routers. There's no extra in there, so there's no need for that designated router election. So don't forget, on a point-to-point, there is no election. On multi-access, which we're going to get into in just a little bit, there is a DR election. Alright, then you get into packet types. Remember, a link state update just says, hey, I need some, or here's some information I had that you asked for. Link state advertisement contains information about the neighbors and paths, just like we talked about. Alright, OSPF uses an algorithm from Dijkstra's method, shortest path first. Just make sure you understand that OSPF uses Dijkstra's shortest path first algorithm. Remember, EIGRP uses dual, OSPF uses Dijkstra's SPF algorithm. And no, you do not have to know that algorithm. Sweet! Alright, again, administrative distance is 110. Don't forget the 5 that you need to know. Connected is 0, static is 1, EIGRP is 90, OSPF is 110, and RIP is 120. Make sure you know those 5 by heart going into the test. Alright, just like EIGRP and RIP version 2, OSPF does provide authentication and encryption mechanics. But we don't have to cover them here. Alright, same topology we're using in our lab. Alright, to turn OSPF on, it's just router OSPF1. Now, this number here after the word OSPF is actually the process ID. It doesn't really mean anything. It's only locally significant to the router. So I can be in router OSPF1, you can be in router OSPF2, the other router can be in router OSPF3, and we'll still all talk to each other. This process ID does not affect the grouping of OSPF. In EIGRP, the autonomous system number does affect the grouping. So in EIGRP, it's router EIGRP1, and I will only talk to other people that are in router EIGRP1. This number here in OSPF has no effect. So the other routers do not have to match, and that's where it gets confusing. This is also why, because of this number being the process ID here, that's also why in EIGRP they refer to that as the process ID as well as the autonomous system number. So don't let that confuse you. In EIGRP it counts, in OSPF it does not. Alright, so then of course you get the same network statement. You have to advertise whatever, you get to use your network statements to pick out which networks you want to advertise, and they still use that reverse subnet mask. But they add one extra piece of information here, and it's called the area ID. OSPF groups everything by areas, where EIGRP groups everything by autonomous system numbers. So with OSPF, the very first area created has to be area 0, and all the other areas have to connect to area 0. So area 0 is kind of like the backbone for OSPF. And as far as the CCNA at this current time, we only do single area OSPF, so everything will be area 0. Now, when the new CCNA exam comes out, they will start doing multi-area, which means you'll have area 0, area 1, area 2, stuff like that. But for now, until September 30th, 2013, it's just area 0. Alright, I know some of you guys are having problems with your network statements, and you still haven't grasped what they do. The network statements, both in EIGRP and OSPF, they're just put on the router to tell the router which networks you're going to advertise to your buddies. And you can only advertise directly connected networks. You can only advertise what you physically know. So router 1 here, he's connected to 2 networks. He's connected to the 10.1.1.0 network over here, and he's connected to the 192.168.1.0 network over here. So on router 1, if I go into the CLI, and I want to make him, participate in OSPF, it's just router OSPF, and I'm just going to do 1, and then network. Now first we'll advertise the serial link, the 10.1.1.0. So 10.1.1.0, and remember the subnet mask is in reverse, so it's 0.0.0.3 space area 0. Let me make that bigger so you guys can see the command. Because I want my router to advertise his networks into area 0. So I put that on there. Now, same thing. I need to go to this bottom network, 192.168.1.0, and then remember, same thing, reverse subnet mask. So instead of 255.255.255.0, 0.0.0.255. And then same thing, I want him to be in area 0. Enter. And that's it. Same thing up here on router 2. Let's make him a little bigger. Oh, I'll just make him router OSPF 2. Now remember, you can have any process ID. I could have made this 1 or 2, doesn't matter. So 10. And I also want him to be in area 0. Boom. And even though I got that message again, you can still keep typing when those messages pop up and break your commands. So at that point, these guys should be good. So if I go here to router 1, and you see how once that first area 0 command came on, they formed that adjacency and they switched it to full. It says, hey, we're going to be neighbors. Alright, so if I get out of here now and do show IP route, you'll see that, hey, I know I'm connected to here and here, so those ones show up in my table. But then I'm also learning about the 192.168.2 network that's up here through OSPF. So OSPF is that simple. The hardest concept in OSPF is learning about the designated router, which we'll get into in just a sec. Alright, I hope that explains a little bit about that network statement again. So moving forward, okay, in OSPF, each router gets its own router ID, and it's used to identify the router through the OSPF process. It's almost like you're giving each router its own name. Now, the router ID command, you can actually assign the router ID with a command. So the first way that the router ID command is applied is you create an IP address and you use that as the router ID command. So I go, router OSPF ID space 1.1.1.1. So I can put any ID I want to on it. If I don't use the ID command, the second way is it's the highest IP address of any loopback interface. Then the third way is it's the highest IP address of an active physical interface. So going down here to router 2, looking at his IP addresses, he's got 192.168.10.0 and 192.168.10.8 network. So this one's going to be higher, the .9, because it's higher than 10, it's higher than 192.8. So if I did not put the router ID command on there, and there are no loopback interfaces on here, then this would become my router ID, 192.168.10. You have to remember this order. Did I manually put it in with the command? Do I assign it with a loopback? Or it's going to be the highest of my physical interfaces. They will show you something like this in the CCNA, and they'll say, hey, no router ID command was used, and there are no loopback interfaces. On R2, what would his router ID be? And you have to look for the highest IP address of an active interface. Don't let that one throw you off. Now, the reason we like to use loopbacks is if I have a router ID, let's say down here, my router ID is 192.168.10.9 over here. If for some reason this link goes down, then this interface is no longer active. That would force my router to change his IP address or his router ID because that ID is not active anymore. So it would have to go, and then it would change my ID to 192.168.10.1, or I'm sorry, 10.2. In OSPF, we don't want the router ID to change. So that's bad. So this is why we use loopback interfaces. I just create a loopback on R2, and I assign the loopback an IP address of 200.0.0.1, and that's going to be higher than all the other IP addresses. Loopback interfaces never go down because they're virtual. If a piece of copper goes down, it does not affect the loopback interface. So my router would never change his router ID. So typically, they want you to use either the router ID command or a loopback interface. They only want you to go to the third one if, for some reason, the other two you can't do or something. So you can find the router ID by show IP protocols. Remember, don't forget how important that show IP protocols is. It shows your K values, timers in RIP, and then your router ID here in OSPF. All right. So again, they're kind of giving you the same thing here. The loopback address should be used as your router ID if you don't use the router ID command. And don't forget how to put the loopback on there. Interface loopback 0, enter, IP address space 10.1.1, blah, blah, blah. Alright, again, just like I walked you through, router OSPF 1, enter. And then if you're going to physically put the ID on there, router ID space IP space address. So router ID space and then the IP address that you want to put on there. And that's how you assign that. Now if you want to clear all that stuff out, it's clear IP OSPF process. So this command here, sorry, I went back. This command here will put the ID on there physically, manually, or you can use a loopback like they discussed here. Hope I made that clear as mud for you. Alright, show IP OSPF will show you your neighbors, or I'm sorry, your different things. Here, show IP OSPF neighbor shows you the neighbors that are connected, the priority of their connected interfaces, their state, what they're connected to, their dead timer, their address, interface, stuff like that. Alright, so show IP protocols gives you the IP or the OSPF process ID, the router ID, and administrative distance. The most important thing being the router ID. Show IP OSPF will give you also the router ID, and then show IP OSPF interface displays the hello interval and the dead interval. You will see something on the CCNA where they show you two routers and they say for some reason these guys are not forming their OSPF adjacency. They're not becoming neighbors. And they're going to ask you why. And they're going to do something like show IP OSPF interface, and they're going to show you the output from both routers. And you're going to have to look through. One of them is going to have like a hello time of 10, one of them is going to have a hello time of 11. Remember, the hello time and the dead time have to match. If they don't, they will not form each other. They don't trust each other. Alright, and again, show IP route, OSPF is showed up as an O. Alright, OSPF, its algorithm uses what they refer to as cost. And cost is typically, if you just do, it's 100 megabits divided by whatever you're going to. So on fast Ethernet, that's 100 megabits or more. It's 100 megabits divided by 100 megabits, so the number is 1. Don't worry about this big 10 to the 8th power divided by bandwidth. It's 100 divided by the bandwidth in kilobytes. So a T1 comes out to be 64. Fast Ethernet at anything that's 100 speed or faster comes out to be 1 or less. Now, you can modify that with the auto cost reference bandwidth command that we'll talk about later. So, Your cost is the total cost to get there. So from R1 to get to this network over here, his cost from R1 to R2, the cost is 64 because this is a T1. And then this is a fast Ethernet line that connects to this network, so that adds a cost of 1. So his total cost from R1 to the 10-10-10 network is 65. So don't forget that, because a lot of times I'll sit there, like I know I did, from R1 to R2, oh, it's a T1, so the cost is 64, so I would put down 64, but you also have to add the cost from R1 into that network, which most of the time is fast Ethernet, and you have to add that extra 1 in there. Otherwise, you will get that question wrong on the CCNA. Alright, again, show interface shows you your bandwidth just like we talked about last week. If I do show interface 000, look at that, blah blah, my MTU is this, and then boom, there's my bandwidth in kilobits per second. Alright, there are two ways to modify the cost of a link. The first way is to go in there and change the bandwidth like we talked about before. And we did that in our last lab. You just go into the specific interface and then you type in bandwidth space, whatever you're going to change the bandwidth to be. Now, after you change that bandwidth, OSPF will have to recalculate that cost. But there's a second way that you can modify the cost of the link that won't make, I guess, OSPF use processor resources. If I go in the interface and do IP OSPF cost, and I put my own cost there, there's no need for OSPF to modify the cost because I physically put it in there anyway. If I modify the bandwidth, I'm modifying one of the variables used in the formula. But if I give them the number, then I'm already giving them the answer, so there's no formula needed. I hope that makes sense. So IP OSPF cost, and that way, let's say you've got one link that you want to specify as the primary, or you've got one that you want to specify as a backup. You can go in here and physically change the cost and make it lower or higher to make that happen. Alright, again, we talked about point-to-point links, and then we're going to talk about broadcast multi-access next. So there's 5 network types, but only 2 of them are covered on the CCNA, point-to-point and broadcast multi-access. Now, point-to-points are pretty easy. It's just all T1s. Every router connects to the, this router connects to him through a single link, and nobody else. There's only 2 routers on this link. On this link, there's only 2 routers. So it's a T1. It's point-to-point from this point to this point. In a point-to-point, there are no designated routers. Every router is kind of almost functions like EIGRP. They just kind of function on their own. But in broadcast multi-access, then you have issues. So here's a broadcast multi-access network. Basically, all these routers plug into the switch, which means this router on his line here has to connect to him, he connects to him, he connects to him. So there's a lot of different connections in here. So because of this, it causes an issue with what they refer to as LSA flooding. Like this. Everybody's sending, this guy's got to send 4 LSAs, one to everybody else. He's got to send 4 LSAs. So all this traffic is being sent through and floods the network when EI or OSPF is trying to converge, which is bad. Consumes a lot of bandwidth, a lot of processing resources, so you don't want this. So the solution is to create a designated router. So everybody decides who the designated router is going to be. Everybody sends their one packet to the designated router. The designated router looks at all the information, then he decides what's best, and then he sends it out to everybody else. Now, when you change to a multi-access network and there's a designated router, your IP address and information changes a little bit. When everybody else sends to the designated router, they send to 224.0.0.6. And then when the designated router talks to everybody else, he sends to 224.0.0.5. So all these guys over here that are not a designated router or a backup designated router, they become designated router others or druthers, however you want to say that. So druthers only speak to 224.0.0.6, and the designated router and backup designated router listen on 224.0.0.6. They're listening for those LSAs. But all the druthers down here, R1, R5, R4, they listen on 224.0.0.5 because that's where the designated router sends that information to. So druthers send to 6, DRs send to 5. I hope that helps at all. Alright, so don't forget, designated routers, the election process does not occur in point-to-point networks, only in multi-access. Alright, so multi-access, and anytime a router connects to two or more routers through the same link, now you have what they refer to as a multi-access network. Alright, so how is the designated a router picked? Well, the first thing is, as all the routers are turned on, the hello packets all go out. The hello packets have all this information there. The router with the highest interface priority. Now, all routers start with a priority of 1, so every interface has a priority of 1. And if you do show IP OSPF neighbors, you'll see the priorities are 1. If for some reason I do not want my router to ever be a designated router, I can change that priority to 0. A priority of 0 means I will not be a designated router ever. Don't ever consider me. Alright, so the first one is it looks at the priority. So if you have not changed the priority, then it goes to the router ID. And remember, the router ID command is set with you either do it manually with the router ID command, or it's the highest IP address of a loopback interface, or it's the highest IP address of an active physical interface. So with the designated router, it's either the highest priority or the highest router ID if no priority has been changed. So if there's a specific router that I want to make the designated router, I want to change his interface priority to 3. And then if there's a router for a backup, I change his priority to 2. And then when all the routers come up, the 3 will obviously be the highest priority and he'll be picked. 2 would become the backup, and then everybody else would be 1s. So remember, the default priority is 1, and then I can change that. Alright, and here's a visit from my son.
Hello.
You gotta say something.
No.
I'm not gonna get any food.
Hello.
Sorry about that. He's usually a lot more talkative. Alright, so moving on. Alright, here's the problem with that designated router election though. It happens as soon as the routers are enabled. So as soon as the interface comes up, they start trying to do this own election. So if let's say I got 3 routers up, but now I'm going to put in a brand new router, and I want him to be the designated router. I can change his priority to 10 or anything, something higher, but it won't happen because the election occurs right off the bat. And once a designated router is elected, he remains the designated router unless he fails, the entire router dies, or the OSPF process fails, like I do the clear IP OSPF process, or for some reason the multi-access interface on the DR fails. So once elected, you're elected for life until you die, basically. Until something dies on that router. Either the router dies, the interface dies, or the OSPF process is cleared from that router. So obviously that's a problem. First router that comes up is going to be the DR, especially if they don't all come up at the same time. So what they want you to do is, in your OSPF network, the first router that you boot up, you need to boot that up first and then wait for a minute, and then he will become the DR. The second one that you boot and then wait for a minute, he will become the BDR, and then you turn on all the other routers. Or you could shut down the interfaces on all the routers, then you can go to the DR and do a no shutdown, then you go to the BDR and do a no shutdown, then you go to all the other interfaces and do a no shutdown. What a pain in the butt. So typically this is what they do. You want to boot the DR first. So if for some reason you've got a brand new router, let's say you got 8 routers on your network, and there's already a DR in place, and you want some new router to be the DR, typically you have to wait till after hours in work. You bring up the new router, you set the priority high, and then you just turn off the DR, and that'll force a new election. Alright, so again, you can manipulate that priority ID with the IP OSPF priority command. And you have to do this from an interface. So I go to interface serial 000 enter, and then from the interface I do IP OSPF priority, and it can be anything from 0 to 255. Now you don't want to go to the highest number right away. You only need to go to 3, and he becomes the DR. So remember, everybody's value is 1. 0 means I cannot become a DR or BR, and then everything else is good. So again, you only need to go to 3, and it's typically that you only want to go to 3 because that way if I want to add a new one down the road, I can just make it 4 or 5, something like that, and I can kind of step this stuff up. But if at the first time I change this, I make it 255, that's going to screw everything up, because then the next one that I want to do, there's no number higher than 255. Your priority can only be 0 to 255. Alright, just like RIP version 1, you can push out default routes to other routers through the updates with default information originate. So the way I've always remembered this, first in our class we covered RIP, RIP version 2, EIGRP, and then OSPF. The very first one, RIP version 1, uses default information originate. The very last one uses default information originate. Everybody else uses redistribute static. So it's almost like default information originate is the bread, and then redistribute static is the cheese and the bologna. So I hope that helps at all. Ray Cisco! Alright, hope that helps you on your OSPF. Again, it's all pretty easy. Just remember, in multi-access networks, there's a designated router elected. The designated router is elected through the highest priority on an interface. Each interface has a priority of 1 by default, and again, you can go in there and change that. But the very first router powered up typically becomes the DR because he doesn't see